Hello everyone. Hope you are doing very well. So, as you all know that today we are going to cover the coordination compounds theory part 5. So, let's begin with our topic, that is NCRT chapter 5, coordination compounds theory part 5, NCRT section. So, today we are going to cover the NCRT section from 5.5.1 to 5.5.3. This is disclaimer. Objective. So today's lecture objective. So after attending this lecture, you will be able to understand the nature of bonding in the coordination compounds in terms of the valence bond theory. So we are going to cover, or we are going to concentrate today on the topic of the bonding in the coordination compounds on the basis of valence bond theory. Let's see the topics that we are going to cover today according to the NCRT. The first is the valence bond theory, subsection 5.5.1. Then the next subsection 5.5.2, which is magnetic properties of coordination compounds. Then our next subsection, that is 5.5.3, that is limitations of valence bond theory. So let's begin with our first topic, that is 5.5.1 valence bond theory. And in this, let's see the inner orbital or a low spin complex. Okay. So in this, let's talk about the square planar complex. Square planar geometry means the coordination number of our complex is going to be 4. Okay, that means the coordination number means there are going to be 4 number of donor atoms or ligands that are going to arranged around the central metal ion in a complex. So let's take this example of complex nickel CN whole 4 2 negative, where the nickel is the central metal and the oxidation state of the nickel is +2. So for the nickel 2 plus ion, the orbitals are going to be like this. Like in the 3D, we are going to have 3D 8 electrons, 4s0 and 4p0. Okay. So 3D 8 electrons are arranged in every d orbital in this manner, in which we obtain 2 unpaired electrons and 3 paired electrons. Total 8 electrons. So here, because in the complex of nickel cyanide or tetracyanide, we have cyanide present as a ligand. Cyanide ion is present as a ligand here, and as per the spectrochemical series, the reactivity or this CN negative ligand is very strong field ligand. So that means it will cause the pairing of the unpaired electrons. So these two unpaired electrons which are present here will going to be paired up like this, you can see. And after the pairing up, we obtain one 3D orbital as the, you can say, empty orbital to undergo in the hybridization to form the dsp2 hybrid orbitals. So one d orbital, one 4s and two p orbitals are going to provide us the hybrid orbitals of dsp2, where the 4 ligands of the cyanide ion is going to donate its electrons like in this manner. So for this complex, which is a low spin complex, that means all the electrons here are having like are paired, so pairing energy is greater here, right? So in the 3D orbital, all the electrons are paired. It is a low spin complex, and for this 1d 1s and 2p orbitals are undergoing hybridization to give us dsp2 hybrid orbitals, where 4 pairs of electrons are going to be donated from the 4 cyanide ligand groups to make the bond or coordinate covalent bond with our central metal, that is nickel here, right? Now if you see the explanation, let's see the explanation for this complex nickel CN whole 4 whole 2 negative. Here nickel is the central metal ion, right? And also the oxidation state of nickel here is +2. You can calculate that like cyanide is having -1 oxidation state, so it you are going to balance the charge. So X for nickel plus 4 times -1 for cyanide is equals to -2, the whole charge present on the complex. From there you can find the value of X, which is going to be 4 minus 2, that is +2. Okay, so nickel is having +2 oxidation state, and the nickel in +2 oxidation state is having D8, that is 3D8 outer orbital configuration. 3D8 means we have 8 d electrons that are going to filled in the 3D orbital. Okay, now you can see in this diagram, when you fill the 3d8 electrons in the 3D orbital, then we focus on the ligand, whether it is strong or a weak field ligand as per the spectrochemical series. So cyanide ion is present as a ligand here in this complex, which is a strong field ligand. And due to the presence of strong field ligand in this complex, it is going to cause the pairing of unpaired electron. That means these two unpaired electrons we got from the 3D8 configuration is going to be paired up like this in this manner to obtain a four paired of or you can say paired of the paired electrons. So from that only we got one empty orbitals from the 3D, and then we take one from the S and two from the p orbital to undergo the hybridization. So 1d 1s and 2p orbitals of the metal will hybridize, and the cyanide ligand, the 4 number of cyanide ligands, will going to donate its electrons here in these 4 hybrid orbitals. Okay, hence this complex is showing the hybridization as dsp2 with a square planar geometry. Okay, so the geometry it is corresponding to with the hybridization dsp2 is square planar, having the coordination number 4, as the cyanide ligand is present in the number 4 here in this complex, and the hybridization is showing as dsp2. That means inner d orbital is participating in the hybridization, so we are covering this example in the inner orbital or a low spin complex. Now let's see the outer orbital or a high spin complex. In this, let's see the tetrahedral complex example. Again, tetrahedral, that means the coordination number will be 4. The geometry will be tetrahedral, but the coordination number will be same as the square planar, that is 4. That means 4 number of ligands are going to be arranged themselves around the central metal ion. So you can see this diagram of the complex MnCl4 whole 2 negative, where the manganese is having initially the atomic number 25, for which the configuration will be 3d5 4s2. Okay, so we arrange the electrons in the diagram here in the 3D and the 4s orbital like this, where we obtain 5 number of unpaired electrons in the 3D orbital and 2 electrons in the 4s orbital, right? Now we see that in this complex, if you see the central metal ion, which is manganese, and if you want to find out its oxidation state, it is going to be +2, right? So manganese is present in the +2 oxidation state. +2 means it is going to donate its 2 number of electrons. So after releasing 2 number of electrons from the 4s orbital, the configuration it got is 3d5 4s0 and 4p as it is, the 4p0. Okay, so why we are considering 4p? Because there are 4 chloride ions that are acting here as a ligand, so we have to we have to take 4 number of orbitals to undergo the hybridization process for the for making the bond with the manganese and between the manganese and the chlorine. Okay, so chlorine have to donate its electron towards the manganese in the empty orbitals of the metal manganese, so it needs 4 number of orbitals, so that's why we are arranging for that. Now manganese 2 positive has 3d5 configuration, where 5 unpaired electrons are present, and there is 4s0 and 4p0. Okay, so for this complex manganese Cl4 whole 2 negative, we got this 3d5 and 4s 0 and 4p0. Okay, where from for this complex we know that chloride ion is present as a ligand. Now chloride ion is a weak field ligand. Okay, because it is a weak field ligand, it does not cause any pairing of unpaired electrons. So the unpaired electron present in the 3D, in the 5, right, 3D 5, so these 5 electrons are remain as it is in the unpaired state. So the empty orbital will be obtained from the 4s and the 4p. So 1s and 3p orbitals are hybridized, form sp3 hybrid orbitals, and in these orbitals, in these hybrid orbitals, the the chloride ion ligand is going to donate its electrons to form the bond or coordinate covalent bond with our central metal ion, that is manganese. If you see the explanation for manganese tetrachloride whole 2 negative, first of all, manganese is the central metal ion present in this, which is present in its +2 oxidation state. If you want to find out, so basically chlorine have -1 oxidation state, so x minus 4 is equals to -2. So x will be +4 minus 2, that means +2. So x value is +2, that means the oxidation state of manganese is going to be +2 in this complex. Now we just write the manganese +2 configuration, and then we focus on the our ligand which is present in the complex. So here we have a ligand chloride, which is a weak filled ligand, and due to its due to the presence of chloride ion as a ligand, which is a weak field ligand, no pairing of electrons will happen among the unpaired electrons. So the 3d5 orbital or 3d5 configuration that we have obtained from the manganese in the +2 state is going to remain as it is. No pairing will happen, and these 4 chloride ions are going to donate its electron from in the sp3 hybrid orbitals, from 1 from 4s and 3 from the 4p. So 1s and 3p orbitals will hybridize together, and the ligand, that is chloride ligands, will going to donate its electrons here in these hybrid orbitals. Hence the hybridization will be sp3 with the tetrahedral geometry, the corresponding tetrahedral geometry. Okay, so these 1s and 3p orbitals are going to arrange themselves in the tetrahedral manner in the 3D space, and hence the complex MnCl4 whole 2 negative will going to show the tetrahedral geometry. Okay, let's see the outer orbital high spin complex for the tetrahedral complex, again having coordination number 4. So let's see this example for nickel tetrachloride whole 2 negative. Okay, now for this complex nickel chloride whole 4 whole 2 negative, we have nickel as a central metal, and nickel is having +2 oxidation state here. So the orbitals of nickel in the +2 uh, charge is going to be filled like this, like 3d8. Okay, and 3d8 means 2 unpaired electrons, and other 3 orbitals are going to have paired electrons. Okay, and 4 is 0, 4p 0. Okay, now we need the empty orbitals for the from the metal to provide the space for the donation of the electrons from the upcoming chloride ligand. Okay, so what will happen, because we know here we have chloride ligand present, which we already seen that this is a weak field ligand, right? So chloride ion is a weak field ligand, and due to which the unpaired electrons remains going to be unpaired, it will not going to be paired up. So these 2 electrons present in the 3d8 remains as it is, as unpaired. That means no empty orbital will be provided by the 3d orbital. So 1s and 3p orbitals from the 4p are going to undergo the hybridization to get us sp3 hybrid orbitals, in which 4 pair of electrons are going to be donated from the 4 chloride ions that are approaching towards the nickel to form the coordinate covalent bond with it. Okay, and so this is a high spin complex. That means here the high spin, the electrons having high spin number is greater. Okay, and the unpaired electrons are present, so this is a high spin complex, and you will get sp3 hybrid where the 4 chloride ion are going to donate their electrons. So if you see the explanation for nickel Cl4 whole 2 negative, nickel here is a central metal ion, so you have to focus on the oxidation state of it, which is +2. Again, you can find out x plus 4 times -1 is equals to -2. That means x is equals to 4 minus 2. That means x equals to +2. The oxidation state of the nickel will be +2. So nickel is in the +2 oxidation state here in this complex, for which the configuration will be 3D8. Now here we focus on the ligand. Here in this complex, the ligand is a weak field ligand, which is chloride ion. Okay, now chloride ion is a weak field ligand. So that means no pairing of electrons will going to happen. So the unpaired electrons present in the 3D8 configuration or 3D8 orbital is going to remain the unpaired, and the 4s and the 4p are going to undergo the hybridization to get us a sp3 hybrid orbital for the electron electron occupation by the 4 chloride ion approaching towards the nickel. So 1s and 3p orbitals will hybridize, and the ligands will donate its electron here in these hybrid orbitals. Hence the hybridization is going to be sp3 for this complex with the tetrahedral geometry. Okay, so the geometry will going to be tetrahedral. That means 1s and 3p orbitals are going to arrange themselves in the tetrahedral manner in the 3D space, and the complex is going to be represent its geometry as tetrahedral, or it is present in the tetrahedral manner. Okay, let's move to our next subsection, which is 5.5.2 magnetic properties of coordination compounds. So let's talk about the magnetic property shown by the coordination compounds. Unpaired electrons in the element or in the complex are responsible for the magnetic properties of the complex. So what we are saying, that in the complex, what will be the number of the unpaired electrons, or either it is present or not, that factor is going to be responsible for the magnetic property shown by the complex. Firstly, the degenerate orbitals will be filled individually with the subshell before pairing up as Hund's rule. So as the Hund rule says that firstly the degenerate orbitals will be filled equally individually, okay, and when they completely filled, when they half filled within a subshell, then the pairing up will going to be start. Okay, so before pairing up of the electrons, the individual degenerate orbitals will going to be filled within a subshell with electrons as per the Hund's rule, and after filling of the half filling of the d orbitals, the pairing of electrons will be start from d6, right? So until d5, you have to fill the electrons in each degenerate orbitals individually, and then when the d orbital gets half filled with the d5 configuration, the sixth electron will be going to fill up again in the first orbital of d orbital for the pairing up. So pairing of electron will be start after the half filling of the d orbital. Magnetic moment denoted by mu can be calculated using the spin only formula for the magnetic moment, which is given by mu is equals to under root n plus 2 Bohr magneton. Bohr magneton here is the unit for the calculation of the magnetic moment, and n here in this formula is representing the number of unpaired electrons present in any complex. If the complex has unpaired electrons in it, either 1, 2, 3, the complex is going to be paramagnetic in nature. And you can also say that if all the electrons are going to be paired, there is absence of unpaired electrons, then the complex is going to be diamagnetic in nature. Let's see the example of a square planar complex showing the coordination number 4. That means 4 number of ligands are going to be present in it. And in this, let's see the first example for nickel Cn whole 4 whole 2 negative. So the complex is nickel Cn whole 4 whole 2 negative, where the central metal atom or ion and its outer electronic configuration will be like central metal atom or ion is nickel with the outer electronic configuration as 3d8 4s2. So this is the configuration for nickel. Now, the outer orbital of metal atom or ion can be shown like this in the diagram for the 3D 4s and 4p. For the 3D8, the electrons are going to filled in the 3D orbital in this manner, where we are getting two unpaired electrons, and 4s2 is going to be filled like this, and 4p is 0. Now we are going to see that what is the oxidation state that is present in this complex for the nickel, the central metal atom. So for nickel here, the oxidation state of it is +2. So nickel in the +2 electronic configuration will be having this arrangement, where it is going to donate, or it is going to release its two electrons from the outermost orbital. So from the 4s2 outermost orbital, it is going to release two electrons in the +2 state, and the 3d8 configuration remain as it is with two unpaired electrons. The 4s from the 2 will become 0 and 4p will be 0. Okay, now we observe the nature of the ligand present here in this complex. The ligand present is the cyanide ligands. So it is a strong field ligands cause pairing of the 3D electrons in the metal, and due to the strong field ligand presence in this complex, the electrons will going to be paired up. So the 3d8 electrons have two unpaired electrons in it, so they are going to be paired up. So outer orbital of metal atom ion in the presence of strong field ligand will be like this, where 3d8 become like this, where all the electrons are going to be paired up, and you got one empty 3D orbital to participate in the hybridization, and then 4s0 and the 4p0. Okay, now the complex is NiCN whole 4 whole 2 negative. The coordination number is 4. That means 4 ligands are going to be bonding with the nickel metal, right? So for that we needed 4 empty metal orbitals, right? So one d orbital, one 3d orbital, one 4s, and 2p orbitals are going to be undergo the hybridization, and we got dsp2 hybridized orbital, where the cyanide ligand is going to donate its electron and form the bond, the coordinate covalent bond with the nickel metal. Okay, you can see no unpaired electron is present in it due to the presence of strong field ligand, the cyanide ligand, and 4 number of cyanide ligand is going to approach towards the nickel, which going to donate their electron in 1d, 1s, and 2p orbital, which is dsp2 hybridized orbitals. Now we see that coordination number for this complex is 4. Okay, so hybridization it is showing is dsp2, like in this manner. So 3d8 in which all the electrons are paired up. Now 1d, 1s, and 2p orbitals showing dsp2 hybridized orbitals are going to be the orbitals where the cyanide ligand is going to donate its electron to form the bond with the central metal ion. So for the dsp2 hybridized orbital, the geometry it is showing is square planar. Okay, so these hybridized orbitals are going to arrange themselves in square planar manner in the 3D space to exhibiting of square planar geometry for this complex. Now the magnetic property, if you observe, because we are talking about magnetic property, so for this complex, for the magnetic property we focus on the number of unpaired electrons present in the complex. So if you see the configuration, we have no unpaired electron present in it, right? So there is absence of unpaired electron. That means n, which represents the number of unpaired electron, n is going to be equals to 0. So the magnetic property it is going to show is diamagnetic, and this complex NiCN whole 4 whole 2 negative will going to have mu, that is magnetic moment, is equals to 0 Bohr magneton, because n is going to be 0. Okay, so the magnetic property shown by this complex is 0 Bohr magneton because of the presence of no unpaired electron. And why it is having no unpaired electron? Because it is diamagnetic and it is having a strong field ligand which cause the unpaired electrons pairing, due to which there is no unpaired electron present in it. So the magnetic property is showing is diamagnetic. Now let's see the example of tetrahedral complex having the coordination number again 4. In this we see the example for nickel CO whole 4. So for the nickel carbonyl whole 4 complex, the central metal atom is nickel and its outer electronic configuration is 3d8 4s2 in the neutral form. Now, for the 3d8 4s2, the outer orbital configuration can be like filled in the orbitals like this. So 3d8 will be like this, where two unpaired electrons will be there, and 4s2 will be this, and 4p0. Okay. Now, uh, we have nickel here in the zero oxidation state. Okay, because a carbonyl ligand is present which cause the metal to exist in the lowest possible oxidation state, or zero oxidation state. So nickel is having zero oxidation state. That means its configuration of 3d8 4s2 remain going to be as it is. So we now focus on the nature of the ligand present. So here we have carbonyl ligand present, which is a strong field ligand as per the spectrochemical series, which cause the pairing of the 4s electron with the 3d electrons in the metal. What does it mean? If you see the diagram, you can understand. So we have 3d8. Okay, because of the presence of strong field ligands, these two unpaired electrons undergoing pairing up. So these two electrons, this one electron will shift here, and this become paired. Now this 4s electron also will go in the 3d orbital, and the pairing will happen. Okay, so this 3d8 will become 3d10, because these 4s2 or electrons from the 4s orbital will also going to be in the pairing in the 3d orbital. So we have already three pairing or three paired electron, they remain as it is. These two unpaired electrons will undergo the pairing, due to which we again get one more paired electron in the 3d 10, and the remaining this one. Okay, so this one orbital, that is empty 3d orbital, in this 4s2 electrons is going to cause the pairing with this 3d orbital, to obtain the 3d 10. Okay, so from the 3d8 we got 3d10 because of the pairing of 4s electron with the 3d electrons in the metal. Okay, so the configuration outer orbital of metal atom or ion in the presence of ligand, this is going to be like this manner: 3d10, all paired up electrons, 4s0 4p0. Okay, now here we count, or we see the coordination number of our complex, that is 4. So 4 number of ligands is approaching towards the nickel central metal atom or ion to form the bond. So we have no d or 3d orbital empty provided by the metal. So the 1s and the 4 and the 3p, the 1s and the 3p are hybridized and give us sp3 hybridization orbital, in which the carbonyl ligand are going to donate their electron to form the bond, to form the codon covalent bond with the nickel. Like in this manner, you can see each carbonyl is going to donate its electron in each orbital from the sp3 hybridization orbital. Okay, so the coordination number is 4 for this complex, and the hybridization it is showing is sp3. So the hybridized orbitals of metal atom in the complex is 3d10 and this sp3 hybridization orbital. In each orbital, the carbonyl ligand, each carbonyl ligand is going to donate its electrons, the pair of electrons, okay, to form the bond. So for this sp3 hybridization orbital, the geometry it is exhibiting is tetrahedral. And the magnetic property, if you talk about, we see the number of unpaired electron. Now if you see the configuration, we have 3d10, that means full filled d orbital is there. That means the number of unpaired electrons is equals to 0. That means magnetic property it is exhibiting as diamagnetic in nature. So for, if you want to find out the magnetic moment using the magnetic moment formula in the Bohr magneton unit, we got magnetic moment value is equals to 0 Bohr magneton for this complex nickel CO whole 4 complex. Okay, so magnetic property it is showing is diamagnetic due to the absence of unpaired electrons in it. Let's see the table for some other examples of having a coordination number 4 are listed. So this table is given here, showing 3 complexes, their central ion configuration, their spin, their hybridization corresponding the geometry and the pair of electrons present in them, and the diamagnetic property they are exhibiting. First complex is nickel CO whole 4, where central ion is nickel in the zero oxidation state due to the presence of carbonyl ligand, and the configuration it is going to show is 3D84S2. The spin it is having is low spin. It is a low spin complex. Okay, that means there is no unpaired electron are going to be present. Okay, hybridization it is showing is sp3, that means 1s and 3p orbitals are hybridized. Geometry it is corresponding to is tetrahedral. These four hybrid orbitals are going to arrange themselves in that tetrahedral manner in the 3 space to exhibit the tetrahedral geometry for the complex. Here the pairing of electron happen. Yes, it will happen because of the presence of strong field ligand, which is carbonyl here. So the pairing of electron happens. Yes, the magnetic property it will show is diamagnetic due to the absence of any unpaired electrons, because pairing happening, so no unpaired electron present, that means the magnetic property it will show is diamagnetic in nature. Similarly, for the second complex, which is given as nickel Cl4 whole 2 negative, the central ion in this is nickel 2 positive with configuration 3d8. Nickel 2 positive means 2 electrons will be released, so from the 4s2, and the remaining electron is 3d8. Spin it is going to show is high spin. Okay, high spin, that means unpaired electrons is going to be present there. Hybridization it is showing is sp3, that means 1s and 3p orbitals are hybridized, and the corresponding geometry it is showing is tetrahedral. Now pairing of electrons happen in this? No, not happen. Why? Because chloride ligand or chloride ion as a ligand is present in this complex, which is a weak field ligand according to the spectrochemical series. So the pairing of it will not cause any pairing of electrons. So that means unpaired electrons is present, and due to the presence of two unpaired electrons in it, the magnetic property it exhibits is paramagnetic in nature. Similarly, for our third complex, nickel Cn whole 4 whole 2 negative, in this the central ion is nickel 2 positive, that means in +2 oxidation state, and configuration is going to be 3d8 after the releasing of 2 electrons from 4s2. The spin it is going to show is low spin. So low spin, that means it doesn't have any unpaired electrons. It does not going to be have any unpaired electrons. The hybridization it is showing is dsp2, that means 1 inner d orbital. 1s and 2p orbitals are hybridized. The corresponding geometry it is showing is square planar, and the pairing of electrons happens. Yes, it happens due to the presence of strong field ligand, that is cyanide ligand in it, and the magnetic property it will show because pairing of electron is happening, so there is no unpaired electron present in it, due to which the magnetic property it will show is diamagnetic. Let's see the example of octahedral complex now. Octahedral complex means the coordination number is going to be 6. In this, let's see the first example for FeCN whole 6 whole 4 negative. So the complex is FeCN whole 6 whole 4 negative. Here the central metal atom or ion is iron, and its outer electron configuration is 3d6 4s2. Okay, so outer orbital of metal atom or ion is going to be arranged in this manner. In each orbital 3d6 having these electron filling where 4 number of electrons are unpaired. 4s2 is this and 4p0. Okay, now we see either we have our central metal ion is having some oxidation state. So yes, here if you want to find out x minus 6 equals to minus 4, that means x equals to 6 minus 4, that is plus 2. So iron is going to possess +2 electronic configuration, for which it is going to donate or release its 2 outer electrons from the 4s2 orbital, and the diagram will become like this. 3d6 will remain as it is with 4 unpaired electrons, and 4s become 0 from the 2, and 4p as it is. Okay, now we observe the ligand which is present. So here in this complex we have cyanide ligand present, which we have discussed that it is a strong field ligand as per spectrochemical series. So the nature of ligand is that it is a strong field ligand, cyanide ligand, which cause the pairing of 3d electrons present in the metal. So the 4 unpaired electrons present undergo the pairing, and the outer orbital configuration become like this. 3d6 remain as it is, but the unpaired electron, that is 4 unpaired electron, remain uh, undergoing the pairing up, and we got 3 paired electrons in the 3d6 and 2 empty 3d orbital, which can participate in the hybridization. And as we know, coordination number is 6, so we need 6 empty orbitals. So 2 is from the 3d orbital, 1 is from the 4s, and then 3 is from the 4p. Okay, so for this complex iron CN hole 6 hole 4 negative, we got 3d6 paired electrons in it and 6 empty hybrid orbitals, which is D2sp3 hybridized orbital, in which the cyanide ligand approaching towards the iron to form the coordinate covalent bond is going to donate its electrons to form the bond. So each cyanide ligand which will going to donate its electron in these 6 hybrid orbitals. So the hybridization, for the hybridization, the coordination number we know is 6. So hybridization it is showing is D2sp3 involving 2d, 1s and 3p orbitals. Okay, so like this, in this manner, the D2sp3 hybridized orbitals, each cyanide is going to donate its electron in each hybrid orbitals, and the geometry the D2sp3 hybridization is corresponding to is octahedral. That means these 6 hybrid orbitals or equilateral hybrid orbitals having equal energy is going to arrange themselves in the 3D space in the octahedral manner, and thus this complex is going to show the octahedral geometry. The magnetic property, if you talk about, so we observe the unpaired electrons present in the complex, and if you see the configuration of 3d6, every electron is paired up, so unpaired electron is absent in this configuration in this complex. So number of unpaired electron becomes 0. That means the magnetic property it shows is diamagnetic. Okay, so complex will be diamagnetic when there is no any unpaired electron is present, and if the unpaired electron is present, complex will be paramagnetic. Now for the magnitude of magnetic moment for this complex, you can apply the formula where n becomes 0 because there is no unpaired electron, so mu will be equals to 0 Bohr magneton. Okay, so the magnetic property this complex is showing is diamagnetic due to the absence of unpaired electrons in it, because it is having strong field ligand which cause the pairing of unpaired electrons present in it, and the geometry it is showing is octahedral. Let's see another example for octahedral complex coordination number 6, which is iron F6 hole 3 negative. So for the complex iron F6 hole 3 negative, the central metal atom or ion is iron. Its configuration is 3d8 4s2. Now okay, its configuration is going to be 3d6 4s2. Okay, now the outer orbital of the metal atom or ion will going to be arranged in this manner for the 3d6, that is 4 number of unpaired electrons and 1 paired electron, right? And 4s2 4p 4d. Okay, why we are considering this so much extra orbital 4p and 4d? Because the coordination number is 6. That means we are needing 6 number of empty metal orbitals, 3d orbitals or d orbitals, or you can say empty orbitals, to for the electron donation by the ligands for the bonding. Okay, so outer orbital of metal atom or ion is going to be 3d6 4s2 arranged in this manner in the diagram in the each orbital. Now iron here is exhibiting which oxidation state? So you can calculate x plus 6 times minus 1 is equals to minus 3, because fluorine is going to have minus 1 oxidation state. So x will be equals to 6 minus 3, that is plus 3. So iron is in plus 3 oxidation state, and plus 3 means it is going to lose its 3 electrons. So 3 electrons, how it will lose? 2 will going to be loosened from the 4s2 and 1 is from the 3d6. So the configuration will become 3d like 5 and 4s0. Okay, 4p0 4d0. Okay, 3d5 means 5 number of unpaired electrons will be there in the configuration. Now we observe the nature of the ligand present, where we have in this complex fluorine as a ligand, which is a weak field ligand. Okay, so this is a weak field ligand. That means no pairing of electron will happen in the 3d or in the unpaired electrons here in the 3d electrons and metal. So that means this 3d5 remain as it is in having 5 unpaired electron, and 4s0 4p0 4d0. Now for this complex formation, iron F6 hole 3 negative, 3 6 fluorine iron ligand are going to be attack on the iron and form the coordinate covalent bond, for which it needs 6 number of orbitals or empty orbitals of the metal for donating its electrons. So we got this 1s, 3p and 2d hybridized orbitals, where in the each orbital each fluoride ion ligand is going to donate its electron to form the coordinate covalent bond with the iron central metal atom or ion. Okay, and the remaining configuration will be 3d5. It is not going, these unpaired electron is not undergoing the pairing up, because there is a weak field ligand, that is fluoride ion, that is forming the bond with the metal ion, that will not cause the pairing of electrons. So we are not obtaining any empty orbital from the 3d orbital. So only sp3d2 from the outer orbital is going to be participate in the hybridization. So the coordination number is 6 for this complex and the hybridization is sp3d2. And you can see this is in this manner the sp3d2 hybridized orbitals are present, where in each orbital each fluoride ion is going to donate its electron. The geometry it is corresponding to is octahedral. And if you talk about the magnetic property, we observe the unpaired electron present. So if you see the configuration, it is having 3d5, that means 5 number of unpaired electron present in the 3d orbital. So n value is 5 here. That means the magnetic property it is going to show is paramagnetic, right? Now if you want to find out the magnitude for magnetic moment of this FeF6 whole 3 negative complex, so magnetic moment will be under root n plus 2 Bohr magneton. So mu will be under root 5 plus 2. 5 plus 2 is 7. 7 times 5 is 35. That means under root 35 will be equals to 5.91 Bohr magneton. Okay. So this is the value for the magnetic moment, and the magnetic nature or magnetic property this complex is showing is paramagnetic due to the presence of 5 unpaired electron in it, and they are remaining as unpaired because of the presence of a weak field ligand, a fluoride ligand, which cause no pairing of electrons. Okay. Okay, let's move to our next section, that is 5.5.3, which is limitations of the valence bond theory. Okay, so let's see the limitations of valence bond theory one by one. First limitation it is showing is that it involves numerous assumptions. Now in the valence bond theory we have so many assumptions. Okay, that means we are talking on the basis of the assumptions, more on the basis of facts. We are only talking about talking on the basis of assumptions. So it involves a various assumptions. So that is the first limitations. Second, it lacks quantitative interpretation of the magnetic data. So the valence bond theory largely a qualitative theory which struggles to provide the quantitative insight into bond energies, spectroscopic properties or the magnetic data of the complex. Okay, it fails to explain the color of the coordination compound. So the valence bond theory doesn't explain that why the coordination compound exhibit color in their compounds. And as you know, that color arises from the electronic transitions between the d orbital electrons, right? So this concept is not addressed by the valence bond theory. It does not quantitatively interpret thermodynamic and the kinetic stabilities. So as I said that the valence bond theory is a theory which largely is a qualitative theory, and it struggles to provide the quantitative insights about the bond energies or kinetic and thermodynamic stabilities of the complexes, of the coordination complexes. It cannot predict the tetrahedral versus the square planar structures in the 4 coordinate complexes. Okay, so basically valence bond theory uses hybridization to predict the shapes of the complexes, of the compounds, right? And it doesn't always predict the exact bond angles. So it cannot predict the tetrahedral versus the square planar structure in 4 number of coordinate complexes. So this is also one of the limitations of valence bond theory. It does not differentiate between the weak and the strong ligands. Okay, so valence bond theory doesn't explain the spectrochemical series. That means it doesn't able to explain the varying strength of the ligands, due to which we are saying either this is a weak or a strong field ligand. So it doesn't able to like explain or differentiate between the weak and the strong field ligands. Okay. And like for the if you talk about these limitations of the valence bond theory, we have observed that first of all, it is having so many assumptions. It doesn't interpret the quantitative data of magnetic properties of for coordination compound. It doesn't even explain the color shown by the coordination compounds, which happens or which is due to the electronic transition of d orbitals, which is a concept not addressed by the valence bond theory. And it doesn't offer mathematical framework to calculate thermodynamic or the kinetic stabilities properties of the coordination compounds. It is more a qualitative theory than a quantitative. It doesn't provide any quantitative insights into these kinetic or thermodynamic stability of the coordination compounds. It isn't able to predict the tetrahedral versus the square planar structures, and because it is this theory is using hybridization to predict the shapes, and it doesn't always predict the exact bond angles or the length. So it doesn't able to predict this differentiate between the square planar and the tetrahedral geometry for the coordination number having 4, okay, in the four coordinate complexes. And also it does not differentiate between the weak and strong field ligands. So the valence bond theory doesn't explain the spectrochemical series on the basis of which we can differentiate between weak and strong field ligand. So it doesn't explain the varying strength of the ligands. So these are the limitations of the valence bond theory. Okay, thank you so much. That's all for today's chemistry session. Thank you.